Today we're going to take a look at section 3.3. Okay, so we did addition and subtraction of whole numbers last time. And this is sort of the conclusion of that. I mean, really, these kind of all could go in one section, but that's too much material. So this is the multiplication and division of whole numbers, and our goal would be to finish the multiplication part today. So we'll see how far we can get. All right, so to start with, just sort of a definition of what we mean by multiplication. For finite sets A and B, if the number of items in set A is A, the number of items in set B is B, and as long as n's not 0, then n times A is all these A's added together n times. If the n value actually is 0, then 0 times A is equal to 0. And finding the multiplication of n, of A times B, is the same thing as finding the number of elements in the Cartesian product, which we had done before, back in, I don't know, somewhere in chapter 2. I think it was 2.3. So here's what we're going to do today, okay? So there are several sections, or several models, I should say, of multiplication. Just like there were several models for addition, there was 2, and there were 4 models for subtraction. You guys remember that? Okay. So last time we got into groups and you guys created some examples before we left. We're going to do that here too in just a second. But for starters, let me actually give you sort of the description of those models, and then you can set yourself up in groups and find out another set or another model example for yourselves. All right, so to start with, repeated addition. So repeated addition is very much the way that the multiplication over here was defined, right? Multiplication n times A is actually A added together n times. So repeated addition is that sort of a sense. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? So if we take 3 tests this Friday and 3 tests next Friday and 3 tests the next Friday, we're repeatedly adding the numbers 3 together, in this case 4 times. And we would end up with 12 tests. But it feels like we are repeatedly adding, right? Yeah, 3 tests this week, 3 tests next week, 3 tests the next week. An array model, used for sets as well. And here would be an example. Minhyu is baking cookies. He is able to place the dough 3 cookies wide and 6 cookies long on his pan. How many cookies will his pan hold? The imagery here is very different than the repeated 3 tests every Friday we had before. Right? Very different. It's the same question. I mean, it's multiplication, right? But it's done from a different perspective. And so this one would actually lend itself very well to drawing a picture to solve it. Let me change my color. So that's my cookie. And it says that I have 3 cookies wide. And that we're going to be 6 cookies long. So that's 2 cookies long, 3 cookies long, and there's 6 cookies long. And you're probably all thinking of a cookie sheet as you did it, right? Absolutely. So this would give us how many cookies? It's a 3 by 6 array. How many cookies would that give us? 18 cookies. Now, an area array, the one we're doing next, is very, very similar to an array. Okay, an area model and array model are very similar. I didn't say that quite right, but it's used for measurement. So something that you can measure. In particular, this is a really sort of a classic example, has to do with creating some kind of a ground space. Alexis is planting a garden. Did you know that, Alexis? Isn't that exciting? Alexa, but we're close, right? So Alexis is right. Yeah, that's right. She has space that's 5 feet wide and 7 feet long. Okay, so we're measuring space, we're not measuring objects. Do you guys see the difference? The imagery is still quite similar, but we're measuring objects in the other one, we're measuring space in this one. And the question is then, how much area does she have in which to plant? So when we draw this, or when we think about giving a way of describing this, an image for drawing works very nicely still again, but we're actually measuring space and we're not actually drawing objects. So this is supposed to be 7 feet long and 5 feet wide. And maybe you can draw yours in a grid format. We'll see how well I do with mine. It's probably going to be terrible. Okay, well there's 5 wide. And that means 7 long. Just watch that. I'll just change the width of my garden. Fabulous. That works one way or another. 7 by 5. So how many feet do I have? 35. And it's square feet because it's feet times feet. It's measuring square space, so it's feet squared. All right, so I had you kind of group up where you already were last time, didn't I? I didn't have everybody sort of shift like serious locations, did I? I don't think so. Okay, so here's what we're going to do. I would like for you to group up with those same people that you were nearby last time. You're going to create 3 word problems, right? That's what these models are. It's a verbal description, a word problem, application problem, whatever language you'd like to use, of these 3 different models. And be prepared to share at least one of them with the class, okay? So, do we have anybody who wasn't here when we did this activity last time? You guys weren't. Okay, so all 3. Excellent. You guys are going to be a group of 3. So, Allie and Alexis and Alicia, because they're all A's, because that's the way it should be, right? So all 3 of you, just find out where you want to shift to. Maybe you guys want to all move back next to Allie because she's got more space, or over here. Well, actually, there's space near every one of you. So find a spot to be. And I will let you guys take a look at these. And while you're taking a look at these, I'm going to go get those test redos. How's that sound? All right. All right. Somebody's going to volunteer. What did you do for repeated addition? Up front, yeah.
Joe buys 2 cookies every Monday. How many cookies has he bought after 5 weeks?
Fabulous. Buying cookies repeatedly on Mondays. Another example of the first one. Okay.
He brought me gifts $10 from her mom every week. How much money will she have after 3 weeks?
Lovely. So we're getting money from mom. How nice of mom, right? So nice. Yeah. All right. How about array? What kind of objects did you put into an array?
Kira's making cupcakes from Hannah's 3 cupcakes wide and 4 cupcakes long. How many cupcakes will her pan hold?
Excellent. That's how big my cupcake pan is too. Yeah. 4 by 3. You bet. Good. Cupcakes in an array. What else? Another example of an array. Mackenzie.
Jack was planting seeds in his garden. He planted 7 long and 4 wide. How many seeds did he plant?
Excellent. So we're in a garden, but we're actually putting objects in, which makes it an array. Very good. Just pausing here for a moment. Did anybody do anything different in an array besides those examples or my cookies? What'd you guys use?
So Cameron collects rocks. So she's able to line them out 4 rocks wide and 5 rocks long. How many does she have?
Okay, so she's putting objects in an array. Can you guys think of any other examples of things that come that way? Like cupcakes come that way. You go and you buy cupcakes, or you put the cupcakes in the pan. Like that's just how they are. Can you think of any other examples of things that are packaged in an array? What was that? Soda. Yeah, definitely. 2 by 6s or 4 by 6s. If 3 by 8s, I don't know. What do they do them in when you have? Is it 3 by 8 in a 24 pack or 4 by 6? I don't even know. What's something? Yeah. What else?
Hershey chocolate bar.
Hershey chocolate bars. Very nice.
I like that. Carton of eggs.
Carton of eggs. Good example. How about toilet paper? Or paper towels even too. Yeah. Yeah, there's lots of things that come in arrays. All right, so examples then of area. Whoever has not spoken gets to give an example now. All right.
Todd is building a pool. He has a space that is 7 feet wide and 8 feet long. How much area is there?
Good. Very nice. Area for our pool. What else do we have? Brooke, did you guys do one?
Yeah.
All right. You don't have to talk since I said your name. If you want to pick somebody else, you can make them talk.
Brooke bought a house. It was a tiny house. The yard was 10 feet long by 12 feet wide. How big is her yard?
That is a very tiny yard. Pretty sure my kids' bedrooms are a little bigger than that one. All right, so we've got the yard space. What'd you guys have up here?
We did a room that's 15 feet wide and 25 feet long. How many square feet of carpet is needed to cover the floor?
Good example. So we're talking about, and you guys did a really good job on the examples of area 2, sticking with a 2-dimensional space. So sometimes I'll have people try to 3-dimensionalize things, and we're not 3-dimensionalizing things. So those were good examples. Any questions about the different models for area? Or not for area, for multiplication. Okay, go ahead and shift your chairs all around, put them back where they go. We have just a little bit more to do in terms of multiplication, and then we'll move on to group work from 3-2. All right, so one of the things we did back with addition is we talked about the different properties that there existed for addition. And then when we got to subtraction, we found out that none of them held. And we're going to do something similar here. We're going to talk about the properties for multiplication, and then we're going to see what happens when we get to division next time. There are the same 4 properties that we had from addition, but there's a couple more as well. So the first property is the closure property. So we talked about this one last time. We talked about the fact that for whole numbers with addition, if you add 2 whole numbers together, you get another whole number. And the reality is that works for multiplication as well. If you multiply 2 whole numbers together, you get another whole number. And that doesn't work with everything. So we did some even odd examples last time, which I thought worked pretty nicely. If you multiply an even number times an even number, do you always get an even number? Yes, so it worked for addition and it works for multiplication. We did odd numbers with addition, and we said, when you add 2 numbers together, do you always get an odd number? And the answer was, no, it didn't work. What if you multiply odd numbers? Then it does, right? So you can't guarantee that just because something works for addition, it works for multiplication. Fails for addition, fails for multiplication. They're not the same operation, all right? So some things work in one context and not in the other one. Whole numbers simply work in both. Okay, even numbers worked in both too, we just found out. Second property is the commutative property. Commutative property is that the order of multiplication, just like the order of addition, doesn't matter with whole numbers. And again, I gave you this example last time about the fact that when you're doing multiplication tables, we'll talk about that in this time, we did addition tables last time, is that it's really nice when you're learning multiplication tables, by the time you get up to your 9s tables, the only new one is 9 times 9. You've done them all, right? 9 times 8, 9 times 7, you already did them because multiplication is commutative, so the order doesn't matter. We have the associative property as well. Looks quite similar. It says that if you have the A, B, and C in the same order on both sides of the equality, right, on the equation, that if you group A and B together or you group B and C together, the product remains the same. And you might be thinking like, but who cares? Well, sometimes it's really nice to multiply 2 numbers together and not so nice to multiply a third one with them. So for example, if you had in your list of numbers a 2 and a 5, I'd be multiplying those together no matter where they were. Because 2 times 5 is 10, and if I have to do another multiplication, I'd much rather multiply by 10 than just about any other number, right? So changing the order of multiplication is often quite convenient given the numbers you have, just depending. We mentioned last time that we had an additive identity, and this one is now a multiplicative identity. So if you're identifying that a property is an identity property, you need to say which one it is. The multiplicative identity property says there is a number, that number is 1, such that when you multiply by it in either order, 1 times A or A times 1, you get back A. It does not change the value. And you use this property when you're solving equations a lot. You multiply both sides of an equation by 7, right? It doesn't change the values, right? Because it's doing the same thing. It's an identity on the equation. So this is an identity on specific values. The value is 1. Here are 2 new properties. First one is the 0 property. The 0 property says that if I multiply by 0, what do I get? 0. And again, it's commutative. It doesn't matter which side I multiply on. A times 0, 0 times A, still 0. And then the distributive property is a combo property. It is used when you have addition and multiplication, or subtraction and multiplication. Okay, it's not a single operation property. So if you have multiplication and multiplication, that's associative. But if you have addition and multiplication, or subtraction and multiplication, that's the distributive property. And what you see happen is that when you have a value multiplied by a parentheses where there's addition or subtraction inside, you're able to distribute over the parentheses, right? Yeah. So what we're going to do next is you're going to take a look at a series of problems and decide which property is being used. So there are 6 of these. Once you've decided which properties are all 6 of them, or you've stumped yourself to the point where you're just not sure which one of the 2 it is or something like that that you're debating between. Once you get to the stopping point here, I'd like for you to compare with a neighbor nearby and see if you chose the same things. Yeah.
You said like on the 0 or the identity property, you have to write out that it's.
Multiplicative identity or additive identity. Yes.
So is that on all of them or just that one?
It's just on that one because it's the only one that actually operates differently because the identity element is different. The identity element for addition is 0, but the identity element for multiplication is 1. And so that's the only one that's super critical that you use the word multiplication or division or addition with it. Once you're finished, chat with a neighbor. See if you have the same list of items, of properties. did you say for the first property? Which one is that? That's right, it's the 0 property. I'm going to abbreviate property. How about the second one? Which one's that? Ah, that's the commutative property. Right? The 7, the 3, the 4, the 3 and the 4 change order. How about C? That's associative property. In that one, the order doesn't change. It's 734, 734, but the location of the parentheses do. What's D? It is. It's the multiplicative or multiplication. That looks terrible. Let's try that again. It's the multiplicative identity property. How about E? That one's distributive. F's a little weird. What'd you guys think F was? It's distributive as well. It's actually taking this entire 1 plus 2 and distributing that through. Okay, that's what's going on. So it's still the distributive property. You can. We don't see it used quite like that. You'll use it. You use it in algebra when you've got variables that you can't combine. It seems silly to do it in this problem because it's just all numbers. I could just add them together already. But within algebra, which is where all these properties eventually land us, right? It works, and it's quite usable there. So, all right. So that's it for the multiplication part of this section. So we'll pick up with division next time.